Hi there, what's going on? So we're going to try out the new camera, the new computer, the new ink, the new everything, and hopefully we're going to answer a couple of questions along the way. The first of all is, what is a logarithm? And we all know that by now, hopefully we know that what a logarithm is. It's a, well, let's see. I think I have somebody that can answer the question for us if we just hang out for a second. So the question is, what's a logarithm? It's a fancy exponent. Yay! Alright, so there you go. That was Shelby. Shelby's our little puppet friend, and making her first appearance in there. So what's a logarithm? As Shelby said, a logarithm is a fancy exponent. And so, you know, log base 7 of 52, we don't know what that is. But we know that if we write it that way, that means that 7 raised to the x power equals 52. Right, this number raised to this base equals that number. So 7 to the x equals 52. We can then take the natural log of both sides, because it's fair to do that, get an answer. A natural log, that's a 7 to the x power, right, way up there. And so I can bring the x down in front, so I get x natural log 7 equals natural log 52. And so x is equal to the natural log of 52 divided by the natural log of 7. And we could easily get some sort of answer on our calculator for what that is. If I had a calculator handy, which I do. Sorry for the delay, I might cut that out, I might not. Ooh, loud noise. So then we just grab the calculator and we take the natural log of 52. Oops. Natural log. Uh-oh, what happened? Put it down. Natural log 52, close the parentheses, divided by the natural log of 7, close the parentheses, and we get 2.03, which seems like a reasonable answer, because if I multiply 7 by itself twice, I get 49, and so if I multiply by it 2.03 times, I get a little bigger than 59, or 49, which is 52-ish. Okay? Same story here. I want to know that 5 raised to the 6x equals 8320. So I'm going to use our tricky natural log on both sides, the natural log of 5 to the 6x. So that becomes 6x natural log 5 equals the natural log of 8320. Dividing, I get that 6x equals the natural log of 8320 divided by the natural log of 5. And then I can figure out that x is all this stuff divided by 6. Okay, and we can solve problems that way, figuring things out as we go. All right, so then, if I'm on camera, off camera, I'm confused. So then we do something like this. Log base 5 of x to the 1, log base 5 of the square root of x minus 4 equals 3.2. So we all know that that's log base 5 of x minus 4 to the 1/2 power equals 3.2. And so then I can bring the half up front, 1/2 log base 5 of x minus 4 equals 3.2, and then to clear the 1/2 out, I multiply both sides by 2, so I get log base 5 of x minus 4 equals 6.4, and then I'm just going to use my properties here, and so that means that 5 raised to the 6.4 power equals x minus 4. So this number raised to this power equals this. Okay, 5 to the 6.4 equals x to the x minus 4. So this is a number. We can get that with the calculator, and then add 4 to it, and we've got x. Okay, so a simple, what looks like a difficult problem, really not that bad to deal with, right, as we go. Ooh, let's use that down now. So what is exponential growth? Exponential growth is growth that is basically, it's when something grows exponentially, it grows in a way that's proportional to the amount that you have. That's the definition of exponential growth. Growth that is proportional to the existing amount. So population growth is exponential growth, because it depends, it depends on how many people are in the population. That's what's going to impact the future population. Money grown in a bank, it grows exponentially, because depending on how much money you have in the bank, you get a certain amount back. Okay. So the other question that we might ask is, what is E? Okay, and let's see if Shelby knows the answer. This is Shelby, yeah. Shelby knows the answer. What's E? The letter after D. Oh, I think my voice changed from last time, but it's the letter after D. No, Shelby, it's actually, it's the exponential constant. Oh, tell us about it. All right. So, I don't know what's wrong with me, but anyway, we'll just continue on. Exponential. What is E? So E is the constant that works with exponential growth. For right now, 2.718. 28, and then it keeps going. It's an irrational number, and we'll talk about where that leads us. So we've seen compound growth. So compound growth with money in a bank. So this is the amount that we have after a certain amount of time. After T years. P is the principal. That's what we start out with. It's that way. It's that way. I'm not sure. That's principal. Principal is what we start out. This is my interest rate. And we want to use that as a decimal, so we would, if it was 8%, we put it in as 0.08. N is the number of compoundings. Per year. Okay. And T is time in years. I'm going to get my little email things popping up. So the number of compoundings per year, that means how often you get interest. Do you get interest once a month? Do you get interest once a week? Do you get interest every day? Whatever. We'll talk about what that all means as we go forward. So there's compound growth versus continuous growth. So compound growth is this way. Continuous growth, we use E. Okay, and so, I don't know where I'm going with this. So this is just doing some comparison stuff. Maybe I'll go back here. So E actually is the limit as n approaches infinity of 1 plus 1 over n to the nth power. Okay, so when we look at this compound growth formula, this looks a lot like 1 plus something over e to the, this looks like it could turn into that. And so for continuous growth, this formula, P times 1 plus R over N to the NT, turns into this, P e to the RT. P is the amount of principal, A is the amount we have after a certain amount of time, R is still my interest rate, and T is time. E is just E, the 2.71828 constant there, Euler's constant. So we could figure out problems like this. How much money are we going to have in the bank if we start with $1,000 and earn 5% interest that's compounded quarterly, weekly, or continuously? If we're doing it quarterly, we use this side. Weekly, we use this side. Continuously, we use that side. And as you play this out, you're going to see if you go through and do this that it's not a whole lot of difference. When we start with $1,000, it's probably change difference between quarterly, weekly, and continuously. But if you've got a bunch of money, then that obviously gets you more money, and so you want the best more money situation that you can possibly get is that continuous compounding. So I'm not going to go through these, but you could just you could plug in 1,000 times 1 plus, in this case, 0.05 over quarterly is 4 to the 4 times 5. 4 times 5 because we're going to get interest 20 times over the course of 5 years. When we're doing it weekly, instead of 4, it'd be 52. So we divide the interest rate by 52 in the other. On the other side, we're going to get 1,000 e to the 0.05 times 4. Okay? Nope, sorry, times 5, because it's 5 years. Okay? And so you can do the comparisons between these, and you see that you get a little bit more money here. With $1,000, it may not be significant, but with tens of thousands of millions of dollars, it would make a difference. All right. So what is A primed? If PERD is my rate of continuous interest, what is A primed? And what does A primed tell me? So I take the derivative of this, A primed. Well, P is just a constant, right? So that's just going to be part of the situation. E, well, what's the derivative of e to the something? The derivative of e to the something is e to that same something multiplied by the derivative of that something. And so the derivative of RT is R, right, if we're doing relative to t. So basically what this is saying is that it is telling you how the amount of money in your bank is changing at any particular time. And it's changing based on, well, the amount that you have how it's growing, and multiplied again by the rate of change at that particular point in time. Okay? So A primed is PE to the RT times R, because the RT is the derivative of R. Now, strike that, reverse it. R is the derivative of RT. I remember that now. Okay? So what it tells you how fast your money's growing at any particular time. If we wanted to know how fast the money was growing 3 years out, we plug 3 in with all the other information. If we want to know 5 years out, how's it changing at that point? What happens if we integrate A primed? Okay. If we integrate a rate, which this is a rate of change, we get a total. So the integral of A primed is going to tell you the total amount of change, not change like dollars and cents, but how much money we've earned, total change in earnings, I guess, or money that we have in the bank, earnings from time A to B. So, you know, if you checked at, you put your money in, and how much money do we make in the first 3 years? We'd integrate from 1 to 3. How much money do we make in years 5 through 10? We'd integrate from 5 to 10 if we have this rate of change. Okay? Okay. So there's this thing called logistic growth, which is another application of exponential growth. And it basically deals with the spread of a rumor, an illness, or a disease, or something like that. And the equation looks like this. Okay? I keep saying okay, but I'm going to just go with it. And what we want to know, a couple things is, well, what's the rate of growth when rate of change at t equals 4? That's what we want to know, and that's the problems we want to do, so we'll just go with that. Basically, what happens with this particular function is t gets larger. So there's some sort of rumor. So what happens is it starts off growing rather slowly, and then there's this period, and my window's not really great. But basically, it starts off sort of, I've kind of got a bad window going. But it starts like this. There's that little flat period, and then it grows really quickly for a little while, and then it levels off. Okay, if we change the window, we get sort of that curve, but I can't get it all in one swoop. So when there's a rumor, you know, it starts slowly, and then those people tell 2 people, tell 2 people, they'll tell 2 people, and then eventually it levels off because everybody's heard the rumor. Okay, or if there's an illness like flu going around, a couple people get it and don't stay home, and so they make other people sick, and then there's more people sick, and then a bunch of people get it, and then eventually, you know, everybody might be sick. Okay, why does that happen? Well, as t gets really large, negative 0.4 t also gets really large, but it gets really large and negative. And e to a negative number gets to be really, really small. Okay, so small that, you know, it's probably going to be close to 0. 0.25 times 0 is going to essentially be 0. 1 plus essentially 0 is just 1. And so this thing levels off at 1.25 in this particular case. It's just a made-up equation for this particular situation. So as time goes on, we level off. That's what's called logistic growth. The rate of change, well, in order to find the rate of change, I would probably rewrite this as 1.25 times 1 plus 0.25 e to the negative 0.4 t. Okay, that's my y equation. So y primed is going to be, you know, well, the 1.25 is coming along for the ride. And this is actually to the negative 1, Mr. Dag. That's what you were all thinking. Why'd you forget that? Because I brought it up to the top, right? And so then this is going to become negative 1 times 1 plus 0.25 e to the negative 0.4 t raised to the negative 2, right? So we multiply by the exponent, subtract 1 from the exponent, and then we're going to have to multiply that by the derivative of 1 plus 0.25. So that's going to be 0.25 e to the negative 0.4 t, and then we're going to multiply by the derivative of negative 0.4 t, which is negative 0.4, right? So it's quite a rate of change. Let's see if I can get a little more space down here. Oh, yeah. Oh, we did all this part already, did that. Talked about that. But didn't miss other stuff down on the bottom of that screen. Should have done that. Full screen. Woo! Special. All right, I'll go back and make sure I didn't skip anything out. So then we could plug in, you know, at t equals 4, we could plug in, we could get ourselves a number for the for how the thing is changing at 4 times in, and it might be a really big number. As t gets larger and larger, it might, you know, it'll get to be a relatively smaller number. So in the beginning, it's going to be relatively small. There's going to be that time in the middle with logistic growth where we're going to get a pretty steep rate of change, and then as t gets larger, we're going to get a pretty close to 0 rate of change because, again, everybody's heard the rumor or got the disease. Well, let's go with the illness. Gotten the flu, and we'll just cross disease off because we don't want that to be the case. All right? So let me see what we got here. Did I skip any other pages? We did do that part. We did all that stuff. We did that stuff. We did that stuff. We've done that stuff, and I think we were pretty well all set as we move through this thing. I didn't write a little story thing for you. Those are the problems that you know about, and I think that is going to cut it for us for this applications of exponential growth. And let's see if Shelby has anything to add. Anything to add? No, all set. Good story. All right, so we'll see you next time. I don't know. Let's see what's going on. Thanks for watching. Hope you learned something, and we'll see you soon. Bye-bye.